Hello, my name is Sahar Semsarha from Team Ariaian, and today I'm going to tell you about friction oscillator problem number 13. This problem is about a motion of the rod placed on the identical parallel horizontal cylinders that rotate with same angular velocity but in opposite directions. Now we're going to investigate this phenomenon. So this phenomenon emphasizes on the same angular velocity but in opposite directions and identical cylinders. I mean, they should be the same. And the problem asks us to investigate the relevant parameters. Here's my outline. First of all, I'm going to tell you about the introduction. So why does this phenomenon happen? Here we have a rod placed on two cylinders. There are three forces affecting this rod: weight, normal force, and the frictions. When the rod starts to move, the weight applied on one of the cylinders will be more than the other one. So it makes normal force 1 to be greater than normal force 2. Then it makes the friction 1 to be greater than friction 2. So the rod will move to opposite direction, and this frequent occurrence makes the oscillation. Now I'm going to explain about my setup. So here we have a rod which is an aluminum rod in this picture, and two car pulleys are used as cylinders. I use a Van de Graaff generator belt in order to connect these two car pulleys, and as you can see here, it is a thread cross in order to provide the opposite direction movement. I use Van de Graaff generator belt because it has low velocity and friction doesn't make it warm. Some holes are used to change the place of the second cylinder as a parameter, and we have two iron rods and a swing motor in order to change the speed of the cylinders. So how did I control the speed of the cylinders? I used a speed controlling device that whenever I pulled it, the speed increased, and whenever I relieved it, the speed decreased. I've collected data with Tracker app, and here we have the chart of the movement of the rod. So according to this chart, the rod is oscillating. Now I'm going to tell you about the qualitative theory part. So the question is that will the rod always start to move or not? The rod will not start to move if we put it exactly in the middle, because the frictions will be equal to each other. But this is impossible experimentally, so always the weight applied on one of the cylinders will be more than the other one, and the rod will start to move, and this will make the oscillation. So now that we know that the rod will always start to move, we can enter the quantitative theory part. Before I start to tell you about the equations, I wanted to mention that this theory contains every condition. I mean, even when the friction coefficient of the cylinders are not the same. But in my experiments, the friction coefficient of the cylinders were the same. So according to Newton's second law, the summation of the normal forces affecting the rod is equal to the weight of the rod. And also we can write normal force 1 and normal force 2 like this, according to torque formula. Then we can write normal force 1 related to normal force 2. By having this and knowing that the summation of the normal forces is equal to the weight of the rod, we can calculate normal force 1 and normal force 2. So now that we have normal forces, we can calculate the frictions as well. So according to Newton's second law, we can write this equation for friction 1 minus friction 2. Another thing that I wanted to mention, which is really important, is that x is equal to x0 plus delta. What does it mean? x0 is a place that the summation of the forces affecting the rod is 0. I mean, it's the place that friction 1 and friction 2 will be equal to each other, and it will be in the middle of these two cylinders if the friction coefficient of the cylinders are the same. Plus delta, which is equal to the distance of the rod from the x0. Second derivation of x is equal to second derivation of x0, because like a second derivation of x0 is 0 because it doesn't change. So we achieved another formula according to Newton's second law. Then we can put these two formulas equal to each other. But we should put x0 plus delta instead of all of the x's we see in the second equation. If you do that, we will achieve this phrase. So in this part, all variables are constant. So we can put these two parts equal to each other and we will achieve an equation for x0. As I already mentioned, in my experiments, the friction coefficients were the same. So x0 was 0. I mean, it was in the middle of these two cylinders. Back to the equation, we can put not constant parts equal to each other as well. If we do that, we will have a differential equation. If we solve this differential equation, I mean, if we calculate the A and B, we can know the place of the rod in each second. So the differential equation have been solved, and we achieved this equation in order to know the place of the rod in each second. The important part about this formula is that here, this part is equal to the domain of our oscillation. And as I already mentioned, x0 is 0 in our experiments because the friction coefficient is the same. And also, I didn't give any velocity to the rod at first in order to meet this velocity part. And if you do not give any velocity to the rod at first, we can cross this p part as well. So the only thing left behind the cosinus will be x0. What does it mean? That means that whenever we put the rod at first, that will be the domain of our oscillation if we do not give any velocity to the rod. So now that we have the domain, how can we calculate the frequency as well? We can do that by calculating the omega. So I've calculated the omega, and by having the omega, achieve this equation for the frequency. So now we can compare our experimental and theoretical results by having this equation right here. So how can we guess our effective parameters according to theory? By having the frequency, we can have the period of oscillation as well. As you know, these two coefficients are constant, so we can guess these two are our parameters. So our first parameter is mu, which is equal to the friction coefficient between the rod and the cylinder. As much as it decreases, it makes the period of oscillation to increase. And our second parameter is d, which is equal to distance between two cylinders. As much as it increases, it makes the period of oscillation to increase as well. So now that we have guessed our effective parameters, we can enter the experiment parts. First of all, I investigated some not effective parameters that I did know it will not affect the equations in the theory. My first not effective parameter was the length of the rod. So I investigated 20 cm and 40 cm for the length of the rod. And here we have the chart of them. My second not effective parameter was the cylinder's speed. The speed of them rotating and the omega of them. The speed of them, when I changed the speed, the higher and the lower speed, the domain and the frequency was approximately the same. And that shows that changing the cylinder's speed cannot affect this phenomenon, and the domain and the frequency will be the same in all cases. My third not effective parameter was the weight of the rod. I put something inside the rod in order to change the weight of it. So here we have the 31 and 68 grams, and the frequency is the same in both of them. Then I investigated some effective parameters like distance between two cylinders. I investigated 15, 20, and 25 centimeter for the distance between two cylinders. According to this chart and theory, as much as the distance between the cylinders increases, it makes the period of oscillation to increase as well. So the frequency will decrease. As much as the distance between two cylinders decreases, it makes the frequency and the frequency to power 2 to increase as well. And this matches the theory part according to this chart. The second effective parameter was the friction coefficient. I put some oil and sugar on the aluminium rod in order to change the friction coefficient of it. And here we have the chart of them. So according to these two videos, the aluminium rod with sugar on it, which has a really high friction coefficient, oscillates really faster rather than this aluminium rod with oil on it. And that shows that as much as the friction coefficient between the rod and the cylinder is lower, it makes the period of oscillation to be higher and the frequency to be lower. So as much as the period of friction between the cylinder and the rod is higher, the frequency will be higher as well. According to the theory, if you do not give any velocity to the rod at first, the first place we put the rod, it must be the domain of oscillation. So I investigated 6 cm and 40 cm first distance from the x0. And according to this chart, whenever I put the rod at first, that was approximately equal to the domain of oscillation, and that matches the theory part. So changing the first distance from the x0, the domain, cannot affect the period of oscillation and the frequency. Here we have a MATLAB code in order to have a simulation for this problem. The output of this MATLAB code was two things. The first thing was this animation, which gives us the press of the rod in each second, and the second output was a chart which compared our theoretical and experimental results. The domain have been given to the simulation as an input, and according to this chart, the frequency and the domain is approximately the same in simulation and experimental results. So here, the domain is not equal to the first distance from the x0. But here is approximately domain is equal to the first distance from the x0. What is the reason? The reason can be because of some errors in our system, as I already mentioned in this animation. What are these possible errors? The first possible error is in that ideal system, the normal force must just affect the rod from the below of it. But in our system, the normal force affects the rod from the corners as well. So that can cause some mismatches in our theoretical and experimental results. And also I'm going to mention another possible error. I've changed the device to the system using motors, but the speed of the cylinder increased a lot when I used motor, so the cylinder and the rod didn't start to move with each other. And there were some disabilities in the rod that it made the doming of it to change a little, or sometimes it made it to fall down. So according to this chart, when I used the motor, the doming was not constant, and it changed a lot, and there were some errors in the doming. But here, in the system I used hand, the doming was constant, and it didn't change. So data taken from the hand are more accurate. But as I already mentioned, because the cylinder's speed cannot affect the frequency, when I used system using motors, the frequency didn't change, and it was correct, just the doming was not constant. So I take my data with both hand and motor device in order to make sure about the frequency number. Now I'm going to tell you about the conclusion. So as a conclusion, first of all, by investigating the forces that are affecting the rod, we achieve this equation for the frequency of the rod, according to the theory. Then we have investigated some not effective parameters like the mass of the rod as I poured something inside of it, and the first distance from the x0, which was equal to the domain of our oscillation. Then we investigated some effective parameters like the distance between the cylinders. As much as the distance between two cylinders was lower, it made the frequency and the frequency power 2 to be higher. As much as the friction coefficient between the rod and the cylinder is higher, it makes the frequency to be higher as well. For example, in the system using sugars, which had a really high frequency, the oscillation was really faster rather than the system using oil. Here you can see my references, and thank you for your attention.